this opportunity to wish the last good morning the online congregation attending the International Virtual Workshop on Global Seismology and Tectonics. As you all know, today is the final day or the day 12 of this marvelous virtual lecture series. I am filled with supreme delight as well as a bit emotional too. However, in the bigger frame, I am highly content with the success and impact of this international virtual workshop. As a matter of fact, this is my maiden attempt in convening an event at such a global scale. Attendees have been the heart and soul of this virtual workshop, as I mentioned earlier, and I thank every single one of you for registering with us and being omnipresent throughout the lecture series. I would like to reiterate that it has been a fascinating journey of knowledge sharing and integration from the finest minds of the world. My sincere acknowledgement to the Honorable Director of CSIR-NGRI, Dr. G. Narahari Sastry, and all the 15 speakers from different parts of the world, and all the organizing committee members for successful conduction of this international virtual workshop. To commemorate the final day of this workshop, today two very big names of Indian geophysics circle will present their lectures. The first lecture of the day shall be presented by Dr. K.Gahlaut from CSIR National Geophysical Research Institute of India, who is going to talking about tectonics of Indo-Burmese arc. So in this function, we are glad to have Professor Ramesh Singh as a chief guest from Chapman University, USA, Professor J.R. Kyle as a session chairperson, and Dr. Saurabh Barua as a session co-chairperson. May I request our session chairperson, Professor J.R. Kyle, for his initial remarks. Over to Professor J.R. Kyle.
Thank you, Shantanu. Thank you so much. Yes, I think it's a big morning for all of us. Dr. Saurabh Barua is there as co-chairperson. Professor Ramesh Singh has joined us, and today's our honorable guest faculty speaker is Dr. K.Gahlaut. I know Vineet possibly since he joined NGRI. It's a long association, and in my experience, he is one of the finest scientists, finest gentleman, and a very warm person I have ever met. I possibly read all of his publications, and I really enjoyed his writing. His writing is so lucid that I never leave any publication to read published by or authored by K.Gahlaut. He is my most respected, I should say, young scientist in the country and finest scientist in this country. Today we will listen to him, and I hand over now this platform to Dr. Shantanu Barua.
Thank you very much, sir, for your initial remarks. Now may I request Professor Ramesh Singh, Chapman University, for his remarks. Over to Professor Ramesh Singh.
Thank you, Shantanu. Greetings from California, and here it is about 9:30, and there in the morning, so you must be enjoying after you are coming after the breakfast, and I have already finished my dinner, but I will be awake, and every day here right now during the COVID-19, we are busy until late night. And Shantanu, he asked me about 2 days back, can you join yesterday? And today I said no, because I had a meeting in Switzerland with the UN, and then I had a meeting with the Japanese colleagues last night, and I got up at 2:30 until 2:30 in the morning. Yes, sir. So first of all, I thank the CSIR and Director Dr. Sastry and Dr. Saurabh Barua, the Chief Scientist, for arranging this virtual workshop on the global seismology and tectonics, which is very, very important. And I must congratulate, and this is a really very good thing for all of us that sitting home, we are attending this important topic. So this is a great thing, and today I'm very happy that Dr. K.Gahlaut, I completely agree with Dr. Kayal. He is a great scientist, and really, especially in seismology. And I was looking today about the Web of Science. And it's no surprise that this guy has published papers in Alaska and Hawaii and with the different groups. And of course, India, you see, whether it is the plate tectonics, the interplate or intraplate, everywhere is represented. And I thought he is a more GPS man, but he has used GPS to understand the tectonics. And when I was doing my graduation, everybody was talking about this Indo-Burma arc. You see, the triangular situations, and this is a very good topic that he is going to talk about the Indo-Burma tectonics, and I consider him the GPS man in India. Okay, so this is a great thing, and I'm sure Shantanu is going to read the bio, but he has got an award, and also he has been given a PRL award. This is what I was checking today. So this is a great thing. But the only thing is he was given responsibility as a director of his Institute of Seismology, and I was very happy that he is heading this institute. But after a few years, and then he left back, and this is very important topic, and I hope the ministry will bring in someone to head this. This is very important. So I do not want to take much time. I want to congratulate everybody in the institute, CSIR, and we should try to arrange such a virtual meeting, which is very important for the Indian people. Because that way, Shantanu told me that 1,000 people are attending, more than 1,000 people every day, whether it is night time or morning time. Okay, so thanks a lot. Welcome to the Vineet, and thanks to Kayal. He is a big force behind this, and he is more than, I believe, 75 years. Very active scientist. Okay, thank you, Shantanu.
Thank you, sir. Thank you, sir. Now, may I request Dr. Saurabh Barua for his words. Over to Dr. Saurabh Barua.
Good morning, everybody. Honorable Professor K.Gahlaut sir, Professor Ramesh Singh sir, and indeed, the GPS man of India, Dr. K.Gahlaut. Convener of this meeting, Dr. Shantanu Barua, my dear participants. When a stalwart like Professor Kayal says he is the most finest and respected seismologist in India, maybe the world, I have no words, sir, to convey you. You have really identified the personality who is really a good, not only a good scientist or seismologist, but also a good human being. He has traveled from Karakoram in Indo-China border to the Arunachal Himalaya syntaxial zone and then dropped down to Churachandpur Mao Fault in Indo-Myanmar region. He loves to travel. He loves to not only travel, but to gather wisdom through his GPS studies. So we are really honored that he has taken our invitation, being a sister from a sister laboratory of Council of Scientific and Industrial Research, National Geophysical Research Institute, the institute which we proud of in Indian scenario, just like ISM Dhanbad and Banaras Hindu University in earthquake science domain. So he is a person who has immensely contributed to the Indian scientific scenario, to the Himalayan region, and without much time, we are eagerly waiting for listen to him on this special topic on GPS studies in Indo-Myanmar region. Thank you so much. Over to Shant.
Thank you very much, sir. Now for our online attendee, let me read out the short bio of Professor Gahlaut. Professor Gahlaut is a chief scientist at NGRI Hyderabad. His research area include tectonics, geodesy, and seismology. He has established GPS network in Andaman Nicobar subduction zone, Indo-Burmese wedge, Garhwal, Kumaon Himalaya, Godavari Fail Rift region, and Koina Warner region. He received his MTech and PhD from University of Roorkee in the year 1989 and 1995, respectively. Before joining NGRI, he served as a lecturer at the Department of Earthquake Engineering, IIT Roorkee, and scientist at Department of Science and Technology. He's a recipient of INSA Young Scientist Award in 1997, CSIR Young Scientist Award in 2001, and MS Krishnan Gold Medal. He was the founder director of National Center for Seismology. Now may I request Professor Gahlaut for his deliberation. Over to Professor Gahlaut.
Thank you. Thanks a lot, Shantanu, and thanks a lot for such a nice thought of arranging this online workshop conference. I mean, it's really remarkable thought and remarkable effort. I thank you to invite me here, and thanks a lot for kind words by K.Gahlaut Dada. I mean, we always call him K.Gahlaut Dada. R.P. Singh sir, we always call him R.P. sir. These two, I mean, I will not talk much about their scientific acumen, but these two guys are truly gentlemen, and that's another reason because of which I respect them. Thanks a lot for kind words. Saurabh is a great friend of mine. Thanks a lot, Saurabh, for all the kind words. So I think I'll start my presentation now. Let me share it. It's not right. It's not there. Yeah. Can you see it now?
Yes, we can see. Yes.
Okay, good.
Yeah.
So, so that's the topic I'm going to cover: tectonics of Indo-Burmese arc. And I chose this topic because I'm involved in this region, entire Northeast region, in fact, for past almost like 20 years. And I mean, I find this region to be very diverse, although the region is very small if you look at the area. But if you look at the variation in culture, if you look at the variation in tradition, language, dialect, tribes, the tradition people, the customs people follow from one place to another place, I don't think there is any other place in the world which is as diverse as Northeast India. I said the region is very small. Northeast India is very small. But look at the diverse nature of this entire region. And that's one thing which I want to point out here. That the way you look at culture, the way you look at tradition, and the way you look at these diversities, the same thing I look at in earthquakes. If you look at earthquakes in Northeast India, which comprises of several tectonic units, and there's so much diversity in earthquake occurrence, there's so much diversity in tectonics that I don't think, at least in Indian plate scenario, I have not seen such diversity anywhere on Indian plate. So that's the topic I'm going to cover, and I will mainly focus on Indo-Burmese arc. But before that, I'll try to. So that's the region I'm trying to cover. If you look at here, just to orient you, so this is Bhutan to the north. So that's the Himalayan arc. Further north is all China. Further north of Bhutan. On this side also you have we have China. On the east we have Myanmar here, and then on the west we have Bangladesh here, and in between it's all Indian. These are the 7 states of country India. So Shantanu and Saurabh are right now sitting somewhere here. This is Jorat, and I'm sitting somewhere deep south in Hyderabad. The tectonic, if you look at the tectonic regions here, so this is the Himalayan arc here, which runs through India, Bhutan, Nepal, and then of course again it goes to Indian region right up to Jammu Kashmir. Just north of it, there's another tectonic unit that's called Shillong Plateau, and by the way, this is the region where the big 1950 earthquake occurred, somewhere here. So that was an interplate earthquake. That was the earthquake which occurred most probably because of interaction of Indian and Eurasian plate in the Himalayan arc. Then we have Shillong Plateau, which we typically consider as intraplate region, and that's where the big 1897 earthquake occurred. So this is typically an intraplate region. This is interplate region here, and then to the east we have a beautiful linear fault which is known as Sagaing fault, which runs all through Myanmar. That's another plate boundary between what we call as India on this side, Indian plate on this side, and Sunda plate on this side. We distinguish the motion of Sunda plate with respect in comparison to Eurasian plate because the motion of the two plates is slightly different. So on just south of Red River Fault, all this region is called as Sunda plate here, and the north of this Red River Fault here, and to the north of Himalayan arc, that region is called as Eurasian plate. So here is a region which is bounded by 3 plates: Eurasian plate, Indian plate, and Sunda plate. Before we actually started this work, sometime in 2003, 2004, we always thought that it's basically the plate boundary is here, which is Sagaing fault, which separates the Eurasian, the Sunda plate on this side and Indian plate on this side. But then slowly more studies came up, geological studies, geodetic, seismological studies, and then we learned some new things about this region. So that's what I'm going to discuss, and that's the layout which I'm going to cover. So I'm trying to I'll try to cover the diverse nature of seismogenesis in the Northeast India. When I'm saying using the word Northeast India, what I meant is the region in the north, in the north, which is Himalayan arc, the northeast syntactial zone, or here it's Mishmi Trust here. Then we have this wedge, Indo-Burmese wedge. Indo-Burmese wedge along with Sagaing fault is known as Indo-Burmese arc. And then in between we have this intraplate region, which is Shillong Plateau. So I'm going to talk very briefly about the diverse nature of seismogenesis, the earthquake occurrence process in these 3 regions. and I said that they are as diverse as the culture of Northeast India itself. Then I will focus mainly on the plate motion and its accommodation across Indo-Burmese arc. So that's Indo-Burmese arc, entire including wedge and the Saline Fault. So that's what I'm going to talk. My talk is not a lengthy one. I have some 15-16 slides, but I'll spend probably more time on each slide. So that's what I'm going to cover. So I come back to the first slide again, and this is what I was saying just a while ago, that there was a big earthquake here, a great earthquake. In fact, the largest in the Himalayan arc, largest known recorded earthquake in the Himalayan arc, which is 1958.6 magnitude earthquake, which occurred which is known as Assam earthquake, but actually it occurred in the Arunachal region. But since at the time Arunachal was part of Assam, so that's why it's called as Assam earthquake. And this was an interplate earthquake. It probably occurred on the main thrust zone. Probably I'll come back in the next slide. Then 1897 earthquake, Shillong Plateau region here, which is where a lot of small earthquakes also occur, and it is still kind of enigmatic as to how these earthquakes occur here. I keep saying that intraplate earthquakes are more complex. Our knowledge, our understanding is very limited when it comes to intraplate earthquakes as compared to our knowledge of interplate earthquakes. Then we have a region which is Indo-Burmese wedge here, and if you look at the color here, so the blue is the deepest and red is the shallowest. So you can clearly see that the earthquakes the depth is increasing. The earthquake depth they're going deeper as you go towards east. So there is a clear evidence of a dipping or a subducted slab in this region. And then, of course, Saline Fault keeps producing big earthquakes now and then. These small numbers here are all the known historical major and great earthquakes, and the size of these earthquakes are, these dots, the filled circles, they are as per the size. So minimum is 4.5 or 5 magnitude here. The biggest earthquake, as I said, is 8.6 here, and then of course there are few earthquakes which have occurred recently. For example, there is an earthquake here which occurred, which is known as Tamenglong earthquake here. I'm just trying to connect with all participants here who are from Northeast. So there's those who are from Manipur. So Tamenglong earthquake is somewhere here where my cursor is. And then this is the Manu earthquake, as we call it, which occurred in Tripura in 2017, if I remember. Yes, this was in 2016, recently, in last 2 years. And then there is another earthquake in Mizoram, which occurred just in June, which is, to me, it's very enigmatic. And I'll try to spend a slide on this. So just to connect with all people, all participants sitting here. If you look at the, so if you see here, so we have interplate earthquakes here, we have intraplate earthquakes here, we have again interplate here, earthquakes here, which occur on the Saline Fault. And if you look at the fault plane solution, they clearly show that yes, there is axial motion involved. So that means the motion along the Saline Fault, which separates the Sunda plate from the Indian plate, or Burmese platelet, as we call it, the region between the two. So that's again an interplate region, and then we have a region here which looks like, and which all these earthquakes look like as if they are interplate earthquakes, but actually they are actually not interplate earthquakes. They're more like intra-slab earthquake. I'm trying to distinguish here between intraplate and intra-slab, because if an intraplate earthquake is which occurs within the plate itself, but if the plate is overlain by another plate. So on like right here we have Indo-Burmese wedge sitting on the Indian plate, and all these earthquakes which are here, they all probably occurs. They all probably occur in the Indian plate, within the Indian plate. So that's why we prefer to call them as intra-slab earthquake. So these earthquakes, they give an impression of as if there's a Benioff zone, but actually these are all intra-slab earthquake. So that's the diversity we have. So we have interplate, intraplate, intra-slab, and then we have earthquakes, which is what that's the reason because of which I pointed this earthquake, Mizoram earthquake, which occurred in June, which I prefer to call as intra-wedge earthquake. If you look at, I'll show you the focal depth of these earthquakes, and it looks like this wedge is overpressured zone, and there are very few earthquakes, or this wedge is generally devoid of earthquakes. But this particular earthquake, which occurred here, it probably occurred within the wedge itself. It was very shallow. I'll come to that. If you look at the fault plane solution, these earthquakes here, they clearly show as if there's a Benioff zone here. But when you look at the fault plane solution, well, you are, in the first look, you're at a loss. That is, there's something very strange happening here. So if you look at the fault plane solution, they don't look like as if they represent the subduction zone, and that's the beauty of this region. These are all, as I said, because they're all interplate earthquakes, so that's why you clearly see a shallow thrust plane here in all these cases. For example, here, and then there are a few. Unfortunately, I missed a few fault plane solution here, but I remember K.Gahlaut showed, probably discussed the Shillong Plateau region, where he showed fault plane solution of in this region. So they're quite diverse here. These clearly show Dexter's slight slip motion here along Sanghain fault, and here there is quite a variation here in the fault plane solutions. So that's the general tectonics we have, and that's the diversity we have in the Indo-Burmese arc. If I come to now, I'll try to cover each of these regions before I actually go to Indo-Burmese arc. So I'll first try to give a slide on interplate earthquakes. For example, I'll start with example of 1950 earthquake, which involved the Himalayan arc here and the Mishmi area here in the Arunachal region. If you look at so this is a recent paper which has appeared in EPSL, and it's very nice to know that Shantanu also is involved in this work. So if you look at the cross-sectional view of this and this region, which is shown here, so this is the main Himalayan thrust here, or the main frontal thrust, which right, when it comes to the surface. So that's the MFT here, and this is where probably all the big earthquakes occur. And what they talk is that in this particular paper, that probably this earthquake occurred. There was a controversy whether this earthquake is a typically Himalayan wedge earthquake or typical, or it also involved the syntactial zone or the Mishmi area also. So, but nevertheless, what the idea here is that this earthquake probably occurred on the main Himalayan thrust. So in that sense, it is a typical interplate earthquakes which occurred because of interaction of Eurasian plate to the north and Indian plate here, and in which the motion on the main thrust zone or the main Himalayan thrust is accommodated through episodic slip during earthquakes, and 19 one of them. So this is typical interplate earthquake scenario, and majority of the earthquakes here all along the Himalayan arc right from Arunachal to Kashmir, they occur. A majority of them they occur on main Himalayan thrust, and that's why we call them as interplate earthquakes. So that's the setup we have in this region. Again, just to orient you, this is where this is where all the coordinators are sitting, Jorat, and so this is all Assam. Then this is Shillong Plateau, and then Indo-Burmese. Now I move to the next region, which is just south of Himalayan arc. So this is the Himalayan arc. This is where somewhere there further up, a 1950 earthquake occurred, and just south, by the way, north is that way. So just south of it is Shillong Plateau here, and as I said that this region we call as intraplate earthquake, intraplate region, because it is within the Indian plate. All these earthquakes which have occurred, for example, the 1897 earthquake, we always have this sort of controversy or debate where exactly the 1897 earthquake occurred, but there are two schools of thoughts. Some people say that it's probably the Oldham fault on which this earthquake occurred, and then there is another school of thought which say that it's probably occurred on Docky fault. So then there is a model here. So this is all Indian plate. So this is the main Himalayan thrust, which is below the Himalayan wedge here, and this is all Indian plate. And then we have this Docky fault here, so which is within the plate, and that's what now, as per this interpretation, a new paper, new interpretation, in which they say that look, this is kind of a subduction of the Indian plate along the Docky fault. Of course, this is being debated now very strongly, and I hope that with new data we'll be able to confirm what is whether this Docky fault actually represents the front of the subduction zone in this case. But nevertheless, this entire region is called as intraplate region. And as I said that this is Oldham fault, so this is as per one school of thought, this earthquake probably occurred on Oldham fault, and since this region is this whole region is kind of uplifted, so that's why we call we refer this region as intraplate region caused by pop-up tectonics. So that's a phrase which a lot of people, including K.Gahlaut, also use quite extensively in their work. So so we have interplate here, and then we have intraplate earthquakes here. Then I come to my favorite region, which is Indo-Burmese arc. So if I show you cross section here, east-west cross sections here, depth sections here, then this is what it looked like. So if you look at, so this is the approximate geometry of the subducted. I'm not using the word subducting, but subducted Indian slab in Indian plate here. This is the plate boundary interface, and if you look at all the earthquakes here, they all occur. Look at the wedge. There's hardly any earthquake within the wedge here in any of the section. Look at here. There are a few here, of course, at 23, 22. So somewhere here there are a few earthquakes here, but then most of these earthquakes, they occur within the Indian plate. So that's why we call them as intra-slab earthquake. These earthquakes, they extend right up to a depth of almost like 150, 170 kilometer. And as I said that if you look at their fault plane solutions, that's the biggest clue what we get about their nature about the nature of these earthquakes. So if you look at the horizontal projection of these focal mechanisms, that's how they look like. But if I take a cross section and I cut these fault plane solution in depth, and I show you a depth cross section of these focal mechanisms, then you can clearly see their fault plane or their nodal planes. And none, in fact, other than this, most of these nodal planes are actually, they don't coincide the plate interface. The plate interface is somewhere here, you can see it, and look at the nodal plane here. None of them they actually coincide with the. In fact, I'm sorry, I should not say none of them, but majority of them they don't coincide with the plate interface. So that means they occur on planes which is transverse or which is orthogonal to the plate interface, and that's why we prefer to call them as intra-slab earthquake rather than interplate or intraplate earthquake. So that's the this is Serine fault, by the way, and you can clearly see that if I cut these fault plane solutions vertically, then you can clearly see that the Serine fault here, which is vertical, almost like vertical or very steep fault, strike slip fault, and all these earthquakes are typically interplate earthquakes. We prefer to call them. We say that this region is Sunda plate. On this side we have Indian plate here, which is and then we have this what we call a subducted Indian slab here, and in between this region, in between Indo-Burmese wedge and Sagaing fault, we call this region as which is known as Myanmar Central Basin. We prefer to call it as Burma platelet. Now it is the same region which continues to the north, goes into Andaman Sumatra region, and that's where we have Andaman Sumatra subduction zone in the frontal arc, and then in the back arc we have Sumatra fault system, and in between these two we have Burma platelet or Burma microplate. There are several names for it. So that's the tectonics we have, and that's the diversity we have. We have all kind of earthquakes, interplate earthquakes, intraplate earthquakes, and then we have intra-slab earthquakes within the Indo-Burmese wedge. I'm sorry. I'm using these words very carefully. Wedge. When I'm using the word wedge, I'm referring to this region, which is the wedge here. When I join this wedge with the a typical subduction like a back arc strike slip fault, then this entire region is I'm referring as Indo-Burmese arc. Yes, I know that Burma is kind of out of fashion, so that's why we have Myanmar on this side. But traditionally, we keep referring this region as Indo-Burmese arc. Traditionally, this entire mountain range here is also known as Arakan Yuma. So these are different names, and although in current political or current social setup, these words are obsolete, but we keep using these words in terms of earthquakes, in terms of geology. Okay, so now I think I'll let me state the problem here. So my problem was, in fact, not my, but that's what everybody was posing. That how do these earthquakes occur? That's number one. What is the role of this wedge here? How does the plate motion occurs between Indian plate and Sunda plate? What is the role of Indo-Burmese wedge? Is the entire motion accommodated along Sagaing fault between India plate and Sunda plate? If that is the case, then how do these earthquakes occur? How do these earthquakes occur here? And why do we have this subduction zone or Benioff zone kind of geometry here? And if we have that kind of geometry, then why these earthquakes are of strange type? They are more on, yes, of course, in a Benioff zone we do see earthquakes like this, but within earthquakes which occur below the wedge, why do these earthquakes they appear as if they are intra-slab earthquake? So what kind of motion takes place along this subduction zone, along this plate boundary interface? I'm sorry, I should not use the word subduction zone because I sort of differ in that sense that we don't call it a subduction zone. So what kind of plate motion occurs on this plate boundary interface, if it is a plate boundary? Whether the motion is accommodated, part of the motion between India and Sunda plate is accommodated partly between Sagaing fault and the Indo-Burmese arc, or an Indo-Burmese wedge. So these were the questions which were which we were, all of us, we were struggling, and to answer these questions, we started putting some GPS in the across Indo-Burmese wedge here. So that was the starting point. So we started this work sometime in 2003, and now we have come to some understanding. But of course, even now the debate is going on. There are a lot of issues which we keep arguing and discussing, counter-arguing. So I'll take you through all those issues, and I'll try to resolve what you can resolve or what we cannot. What is fact, and what is fiction. So, but to make my point straightforward, what I want is that I want everybody to sort of realize that as I said, that if you look at the first statement, that all these seismological studies, the main purpose here is for bureaucrats, for common public, other than our own academic interest, but the main purpose here is to understand the seismic hazard. What is the earthquake potential in a particular region? So that's the whole crux, that's the whole motive of all these seismological studies. And then we try to understand what is the geometry of the crystal, what is the geometry of these faults, which are hosting or which accommodate the plate motion, or in other words, in our jargon, what is the strain budget in that region? And that's where so we have a lot of seismological methods which try to help us in understanding the crystal structure through their imaging techniques. And then we have GPS measurements, which helps us in understanding the strain budget, which helps us in understanding the plate motion, which helps us in understanding how much motion is accommodated by each and every of these fault zones. But what is important here is to quantify this strain budget. The first and the foremost thing is to understand the relative plate motion. What is the relative plate motion between India and Sunda? And that is defined by longer plate circuits, what we call as long-term, long-distance plate circuit. So what we do is we don't go close to the fault, because we know that all the deformation is generally concentrated close to the fault, and as you move away from it, that's what the elastic rebound theory says, that the deformation is basically focused close to the fault, and as you move away from it, you actually the motion actually represents the motion of the plate. So it's very important to if you want to understand the strain budget in this region, it's very important to understand or to know what is the relative plate motion between India and Sunda. Now that's a big challenge. The relative plate motion will not be dependent totally on GPS measurements, because GPS measurements are site measurements, and each and every of your site could be influenced by several geological processes, in fact, sometimes anthropogenic process, or sometimes even hydrological cycles. So we need to make sure that the sites which we are using to define the plate motion, I'm not taking the contribution from. So in that sense, it's very important to have a robust estimate of relative plate motion. I'm emphasizing this here because that's the problem we found in one case. And then so you need to tell whether the motion here is, for example, is 36-37 millimeter per year of India plate with respect to Sunda plate, or the motion is 44 millimeter between India and Sunda plate. So it is this motion which which needs to be accommodated along these faults. And it is this motion which will define the seismic hazard of the region. It is this motion whose nature of accommodation, whether it is aseismic or whether it is elastic, whether it goes into elastic strain accumulation leading to stick and slip motion on the fault, which will define the hazard potential of the region. So it's very important to define what is the relative plate motion in a region. It's true in all in all plate bound regions of the globe. It's not that I'm not just talking about Indo-Burmese wedge, but that this is a truth in all cases. Then comes that, okay, now I have this, I know that this is the relative plate motion between plate circuit between India plate and Sunda plate. Then how do I accommodate it along these faults? Is the motion, for example, in this case, Sagaing fault here and there's another fault here, for example, K.Gahlaut fault. Just for the sake of example, is the motion being accommodated by these two faults? So maybe Sagaing fault here and the K.Gahlaut fault here. So the sum of these two algebraic sum of these two is the relative plate motion between India and Sunda. Is that the case, or the motion is partitioned? So this is not partitioning, but this is a distribution of plate motion along two parallel faults in the similar manner. So you have Dextral motion here, you have Dextral motion here, and the sum of these two is nothing but the relative plate motion. But then there could be another case which we call as slip partitioning, which is typically which you see in Andaman Sumatra region, wherein you say that, okay, we have this Sagaing fault here, which is accommodating majority of the motion, and then there is some reverse motion or thrust motion which is occurring. I'm just giving an example, which is occurring Indo-Burmese wedge, which is here, and the resultant of these two is the relative plate motion. So it all depends. How do you? So that's why the importance of quantifying this relative plate motion, because that's what is going to define the slip budget or the strain budget in all these regions. And this is what and we will be able to sort of identify which are the faults which have potential to generate big earthquakes, whether they're strike slip type or whether they're reverse type. So that's the importance of defining plate circuit and then breaking it into its component. So starting with this, that was the background. So that's what we did that's what we started in sometime in 2003, 2004. We installed a GPS network here. So that's so again, I'm saying Gerard would be somewhere here. So this is the Indo-Burmese wedge, and we put a lot of GPS stations here, and then we estimated their plate motion with respect to India, and that's what we found. Let's not go into the detail of all this analysis here, but just look at the plate circuit here. So we know that the motion of India plate with respect to Sunda plate is about 36 or 37 millimeter per year. In this case, Sunda plate. The motion of Sunda plate with respect to India is about 36 millimeter per year. And then we said that, look, we know it for sure now because there are a lot of geological studies and now, of course, geologic studies also, even during 2003, which indicated that the motion which is accommodated at Sagaing fault is of Dextral type, and it is about 20 millimeter per year. And then we found that the remaining 18, if you look at the motion which is being accommodated in this region, then we found that there is a fault which is known as Churachandpur Mao fault. It's not that we discovered this fault. This fault was already known, but we have no idea whether this is the culprit in the Indo-Burmese wedge, in the sense that it is this fault which is accommodating the motion here. So we found that it is the Churachandpur Mao fault, which lies on the western edge of the Imphal Valley here, and which runs across which runs through all this Indo-Burmese wedge, and it is this fault which accommodates a motion of about 18 millimeter per year. Now, this was to us, it was a surprise. The next surprising thing here was that the motion here is mostly aseismic. If you look at the vectors here on either side of the fault, you clearly see a sudden increase in the velocity. You clearly see a sudden jump in the velocity. So that now this is not expected from a fault which is accumulating strain. So then the next result from this was that okay, this fault is probably mostly aseismic. So we could define the plate circuit, we could break it, and then we could see that where exactly in the Indo-Burmese wedge, where the fault, which fault is accommodating it, and what is the nature of this accommodation. So we said that it's mostly aseismic. So that was the story until 2013. But then there was a lot of good work which was done in Bangladesh side. So there was a network which was installed here by Bangladesh and US together, and what they found. So that's a network they had. That's the network they had. So they said that you remember that in our time there was no information from this region, and we could satisfy this plate circuit only with two the motion on only on two faults, Saline fault and Churchandpur fault. But then the data came from Bangladesh, and then they said that look, the motion, even this part accommodates some of the motion. To us, it was a problem, in the sense that we thought that the plate circuit, we could accommodate all the motion which is required by the plate circuit, but then the data from Bangladesh is suggesting that there's some leftover motion here which is being accommodated through reverse motion, and that was and it had huge seismic hazard implications, because as per them, they suggested that yes, of course, what was said in the earlier paper, that yes, Churchandpur fault certainly accommodates the motion, and it is mostly aseismic. Saline fault also accommodates lots of motion, which is recoverable. So that means earthquakes do occur there. But then there is a gradual decrease in the plate motion towards west, and if you fit a curve in this, then the curve is consistent with strain accumulation on a thrust fault, on a gently dipping thrust fault here, and that led to conclusion by Steckler that probably there is a subduction which is going on here, and so then there is this third component which came. I mean, we thought that it's only saline fault and CMF which is doing the trick here, which is accommodating the motion, but then they introduced this. There's some subduction which is going on in this region. By the way, as I said, we didn't have these observations here, but then we were kind of puzzled that what went wrong with our results, and then we suddenly realized that probably what they have done is they have not defined the plate circuit. What they are saying that the motion between India and Shan motion, it's not India Sunda motion. So that means Shan plateau is here. So it is possible that rather than defining the plate circuit, they said that no, let's look at only the motion between India and Shan plateau. Now, to us, we thought that this is something which can be debated. We thought that this is slightly problematic, because that means if that is the case, then as you move southward, the motion between India and Shan plateau is going to change, because here what most of these sites here in Shan plateau here, they are influenced by the toroidal motion which occurs around the northeast Himalayan syntactical band. That's along which the Tibetan plateau tried to extrude, and as you go southward, the motion decreases. So that means the motion of Shan plateau is not uniform all through. So if you take sides here, the motion is going to be large. So India Shan motion is going to be large, and if you are somewhere here, somewhere in the middle segment of the Sagaing fault, that motion, the motion of Shan plateau is going to be less. So then we have a problem. So that means we thought that probably we need to work on defining the plate circuit first. That's very important. Otherwise, we will be incorporating the motion which is caused by other processes. In this case, the extrusion of Tibetan plateau towards southeast. So that to us that was a problem in defining the plate motion here. So what we did was that, okay, let's now, since these data are published, these data are available. These data are available. Can we try to modify our results which were here? Can we try to look at the plate circuit again with the new data? And that's when we came up with a paper which came up just last week, in fact last month. So then we could see that, yes, of course, what they said is yes, probably right, partly, in the sense that yes, this region is accommodating some motion because I can see some gradient here, but the motion between India and Sunda is not as large as this much as they defined. They said a motion of about 44 or 42 millimeter per year. So the actual motion of India and Sunda, what we did was that we actually analyzed a lot of data from Sunda plate. We defined the Sunda plate, then we defined the Indian plate, and then we sort of redefined, and then we calculated the angular velocity between India and Sunda, and that's when we came up with this number on latitude somewhere here 24, that the motion of about 37.6 millimeter per year is the motion between India and Sunda. We also analyzed data from Sagaing fault, the new data which keeps coming up. So that again found up the motion as 20 millimeter per year on Sagaing fault. We confirmed that yes, the motion on Choisang fault is about 16 millimeter per year. We still have issue whether the motion is purely a seismic or it is also log, because we found that the combination of the two, the shallow portion being creeping and the deeper portion being log, fits the data quite well. So there is still an issue with the motion on CMF. But then to support the argument of the earlier paper, we found that yes, of course, this plate circuit requires a small motion of about 7 millimeter per year to be accommodated on the blind mega thrust here. We call it blind mega thrust, which mostly lies below Bangladesh and part of Tripura. But then the problem here is that they thought what they suggested was that this entire motion here is purely because of elastic strain accumulation. But when we actually looked at the scatter in the data, we found that you can fit anything in this. You can either fit a strain accumulation curve here, or you can fit a creeping fault here, a motion which is purely a seismic. So I mean, this is a problem with this region itself, because the entire region is filled with sediments. Ensuring the benchmark stability is always an issue in this region. So that's why there's a lot of scatter in the data. So at this point of time, yes, there is some motion which occurs on the blind megathrust here, but we are not sure whether it occurs through locking, strain accumulation, or it is through a seismic creep. So there's still a doubt about seismic potential hazard in this region. So that's the story which we came up 2 weeks on last year, and which was published last month. But then there was an earthquake which occurred in. So again, I said that as I said earlier, that this wedge, there's hardly any earthquake within the wedge. All these earthquakes, they occur within the Indian plate. They don't occur on the interface, but they mostly occur within the Indian plate. So that's why we call them intra-slab earthquake. And this motion is largely a seismic. But that's where we found an issue. That there was an earthquake here in Mizoram, which occurred on June 22nd this year. So that's the earthquake here. And if you look at the fault plane solution here, it is typical strike slip, Dexter strike slip on this plane. And if you trace the CMF, you can trace it up to here, but beyond this, we do not know how does it go. There's not much work which has been done either from Indian side or from Myanmar side, because it's basically a border region. So we do not know how the CMF actually moves here, how the CMF can be traced here. Initially, we thought that this earthquake probably, so this is the epicenter. These are the various estimates of epicenter by various agencies. Initially, when this earthquake occurred, we thought that there's a fault which is known as mud fault. So probably mud fault is the culprit, which is transversed to the Indo-Burmese wedge. So that's where the earthquake occurred. But actually, there's all these estimates of epicenter and all the aftershocks, they don't coincide with the trace of mud fault. All of them are almost like 20 kilometers north of the mud fault, and they're much closer to the trace of CMF if we extend it southward. So probably this fault, this is CMF. So here is a case which is quite common elsewhere in the world and all on many strike slip faults or even subduction zone, that it's not necessary that the entire trace of the fault is a seismic all through its length. There could be certain patch which could be seismic, which could be active, seismically active, which could be which can accumulate strain. Some part of it, some section here could be accumulating the plate motion aseismically, but then there could be some segments where the motion could be active, seismically active, and that this is probably one evidence. So now we have again sort of, that's how the evolution takes place. So from no fault we came to CMF, from 2 faults we came to 3 faults, and then from each and every event is telling us, is adding a new paragraph in the whole story. And this particular earthquake, it has added another paragraph in saying that it is not necessary that a CMF is aseismic all through its length. It is possible that you can have variation along the in the nature of the plate motion along the fault. That's what we have seen at San Andreas fault, for example. That's what we have seen at Anatolian fault, for example. So this is a common thing which happens here. So that's so as I said that if you look at the Tripura earthquake, Manu earthquake, or which occurred here in 2017, an earthquake which occurred in 2016, the fault plane solution looks similar, but their depth, in this case, both these earthquakes were probably close to 30 kilometers, all of them, both of them. But this earthquake, it occurred 8 to 10 kilometer depth. So that means this earthquake is quite different from, it is not an earthquake which is, these were intra-slab earthquakes. These earthquakes occurred within the subducted Indian plate, whereas this earthquake occurred within the wedge on the CMF. So in that sense, this earthquake is probably different from the intra-slab earthquakes which we generally encounter, which we generally see here. So that's the last thing which we wanted, which we have added now. That yes, it is possible that it's not necessary that this CMF is purely a seismic. There could be some portion of it, some segment of it, which could be accumulating strain. So the whole idea here is how to confidently, robustly estimate the seismic hazard along a fault. So here we could see that, okay, we have Sagaing fault, CMF, and then of course the blind mega thrust, and then we said that CMF is mostly a seismic all along its length, but then now we are kind of modifying our statement that it is not necessary. There could be some segments of the CMF which could be seismically active, and that requires more data collection, that requires more instrumentation, that requires better monitoring. It's just a chance that we saw this earthquake of Mizoram, but I'm sure there could be more earthquakes if we look them carefully, the earthquakes which occurred in this region. If we are sure about their fault resolution, if we're sure about their focal depth, then it is possible that we can find more such earthquakes which tells us that, look, it's not the CMF is a seismic all along its length. There could be some segments which could be seismically active. So I think we have come a long way from the oldest plate circuit which we defined in 2013. Then this came in 2016, and then finally now this is what we have. That it could be logged and some portion, and there could be some segment which could be creeping. So that's how the evolution has gone through. By the way, I mean although this is the work which we started almost like 20 years back, and in fact there are 3 generations which are involved in this. Myself, then Bhaskar, very bright student who was with us. Now he's a faculty at NIT, so he was involved in this. And now this guy Panda is the student of Bhaskar. So there are 3 generations which are involved in such work, and that's how the evolution takes place. That's how the evolution has taken place as per Darwin's theory. So we need to continuously work on it. We need to continuously refine our statements through more data. Each and every earthquake is unique. You just need to turn it around, and then you will find something new, something special about that region, something special about that earthquake, which will tell you something more about the region, about the tectonics of the region. So that's where I want to end here, and I'm absolutely fascinated by the beauty of Northeast India. I mean, you go to each and every region and you find something different. The culture is different, the tradition, the dialect. I mean, I was surprised when I started going to Manipur first. There are more than 20 dialects. There are more than 20 languages within Manipur state, and that's the beauty of this region. And that's the same beauty. That's what I see in the earthquake occurrence processes. Thank you very much.
Thank you very much, sir, for nice deliberation. You have nicely reviewed.
Can I stop the presentation, or should I keep it on?
Sir, it's up to you, sir. It's up to you. Yeah. Thank you, sir, once again.
If somebody wants to ask.
Thank you once again. You have rightly reviewed the seismicity of Indo-Burma ranges with a thorough discussion of the GPS measurement of crustal deformation and their constraint on the tectonics of the region. Now we may have some short comments from our chairperson, from our chief guest, and from our co-session chairperson. May I first request Professor Ramesh Singh sir for his comments. Over to Professor Ramesh Singh.
Okay, Shantanu, this is a really great lecture by Dr. Gahlaut. I would like to compliment him because we are talking about generation to generation in understanding the seismicity of the Indo-Burma. Because the weakness of the Indian people that they do not promote generation and generation. So as he told Dr. Panda and then other guy, okay, and they're working there. So this is a great thing, and we should learn this, and we should promote our students to work on this to understand this Indo-Burma region. And if you don't mind, I would like to ask him, because he is a GPS guy and he delivered this talk on the tectonics and deformation. Okay, and Vineet, can you tell us how many GPS stations you have there deployed?
At this point of time, we have almost like 20 stations in Shillong Plateau and Indo-Burmese West region.
Okay, the question is
these are permanent stations.
Okay, thank you. The question is 37 millimeter per year, which is a very fast movement. And when I see California, we have so many GPS, and here you are talking about the 1200 kilometer, right from 20 degree latitude to 20, I believe it, 16 to 28. So you are like Dr. Sri Hari is here, director, Santanu is there, Saurav is there, and since they are very close, and we should expand this network to understand the whole deformation, because you never know when the big earthquake will come. So thank you very much for the giving illuminating talk for the new generation. I'm sure the new generation will learn from this, and they will really try to work in this region. So thank you very much.
Thank you, sir. Now may I request our session chairperson, Professor J.R. Kyle, for his comments. Over to Professor J.R. Kyle.
Oh, thank you, Shantanu. Thank you, Professor Singh, for your appreciation of this work. And yes, as we all expected, this is very exciting and very enlightening lecture by Dr. Gahlaut. So wonderfully he has explained, as I said, very fine scientist, very scientifically, without any bias, very rationally, he has made us to understand what is happening here. It is a wonderful lecture, Dr. Vineet. Now I have a small query. Are you referring both the Manipur earthquake 2016 and the Mizoram earthquake 2020, both are caused by the CMF?
No, it doesn't look like that way, because the Tamenglong earthquake is almost like 30 kilometers west of CMF. I have gone to Tamenglong, the place where this earthquake actually occurred. I did a lot of mapping in that region after the earthquake also. So this earthquake, the 2016 earthquake, did not occur on CMF for sure. That's number one, as far as the distance is concerned. Number two, the depth of the earthquake was itself was of the order of almost like 30 kilometers. So that means this earthquake occurred, and then since it did not occur, if you look at the fault distribution also, which is very well constrained, it doesn't look like to be coinciding with the trace of CMF. So yes, Tamenglong earthquake probably did not occur on CMF.
Okay, so because your initial report on Manipur earthquake was on CMF, so now you think that Manipur earthquake was not on CMF. Is that, am I right?
Oh, if I gave that statement somewhere, please forgive me. I mean, if I said that way, no, there's something wrong. If I said that way, no. See, Tamenglong earthquake did not occur on CMF. No.
Okay, okay. Thank you so much. I think there will be lot of interesting questions. So you look forward to your interaction to those questions. So now over to Shantanu, please.
Thank you, sir. Now, may I request Mr. Prasidjo for the question and answer session.
Thank you, sir. With your permission, I'm going to read out the question. The first question is, it is not clear as per definition why Sagayan fault is considered as a plate boundary fault.
Okay, so as I said that the motion between India and Sunda is about 37 millimeter per year, and part of it is accommodated on the Sagaing fault. Sagaing fault takes about 20 millimeter per year, and if you look at the earthquakes, they clearly suggest that yes, Sagaing fault is active all along its length, and the fault plane solution clearly suggests that there is a axial motion which is going on. So yes, Sagaing fault certainly defines the eastward, the most easternmost boundary of this Indo-Burmese arc, and the moment you are further east of it, then it's all Sunda plate. So Sagaing fault certainly is a plate boundary fault, but the only issue what I'm saying is that it's not the only plate boundary fault. So the plate motion between India and Sunda is accommodated or partitioned between Sagaing fault and through a Chandpur-Mao fault and the blind megathrust.
Okay, sir. The next question is the Great Assam earthquake of 1950 really an Himalayan earthquake?
Well, that's a very intelligent question, and I'm sure that the co-author of the paper, Shantanu, which is sitting here, should answer this. But nevertheless, yes, we have this which keep bothering us, whether 1950 earthquake was typically a Himalayan wedge earthquake, which probably occurred here. But then, if you look at the Mesoseismic region, if you look at the landslides, if you look at the aftershock, they clearly suggest that, well, even this region was also involved. Yes, if you look at the fault plane solution, it is typical of Himalayan wedge earthquakes. It is typical of an earthquake which occur on main Himalayan thrust. But if you look at the extent of the rupture, yes, part of the Himalayan wedge and part of the Mishmi region was also involved. Unfortunately, 1950 was the period when we almost got freedom. Our instrumentation was coming up. So although this is the last big earthquake, the latest big earthquake of the Himalayan arc, but our instrumental record of these earthquakes are very limited. Because of the remoteness of this entire region, people could not go much in this region, and because a lot of damage also occurred in the neighboring China region. So because of the international border issue, so although it is the largest Himalayan earthquake or earthquake of this convergent margin, if I can correct. So the latest earthquake, but even then our understanding of this earthquake is poorer than other Himalayan earthquakes which occurred before 1950. So that's yes, of course, that's an issue which we have. So we still do not know for sure whether it is typically Himalayan wedge earthquakes, but since part of the rupture certainly occurred on the Himalayan arc in this region, So yes, of course, I mean, it was a Himalayan earthquake, but then of course part of the rupture also occupied this region.
Do you suggest there is another plate between Kabul and Sagayan fault?
We did not find any motion, any significant motion on Kabul fault. So in fact, there are no data as of now, but I know that there are a few more GPS stations which have been installed in Myanmar. So in few years' time, we will be able to know exactly whether why I'm not able to. So you can clearly see here that there's hardly any motion between, on sides to the west of Kabul fault and to the east of Kabul fault. So as such, it doesn't look like as if Kabul fault is accommodating some of the motion. But I mean, no, probably you also realize that there are no GPS stations here. There's hardly any coverage here. So probably yes, it could be accommodating some of it, but lack of data does not allow me to say that KBF is accommodating some of the motion.
Okay, sir. The next question is: deep of Kabul fault is again towards west. Is it also confusing? Can you highlight on it?
Yeah, I agree. I mean, that's a mistake which has been done here. The French group suggests that this fault, Kabul fault, is actually dips towards towards west, whereas if you look at a lot of work by our Indian scientists, they have shown Kabul fault to be dipping towards east. Logically speaking, if you look at the topography, if you think that the topography is partly the result of tectonics, then logically yes, it could be dipping towards west. But again, this is something which requires investigation, whether the Kabul fault is an east dipping fault or a west dipping fault. But logically, yes, it is. I'm sorry that we have drawn it wrongly. It should be dipping towards west as far as logic goes.
The next question is Shillong earthquake 1897. May we call it intra-slab earthquake?
No, we don't. As I said that we call these earthquakes as intra-slab because over this we have wedge here, the Indo-Burmese wedge here. So that's why, and then the Indian plate, the upper plate is somewhere here. So that's why we, and all these earthquakes, they occur here. So that's why we call them intra-slab earthquake. But here, it's all it's all Indian plate here. I mean, these rocks here, they're all part of Indian plate. So it will not be proper to call 18 and 7 as an intra-slab earthquake. It is typical of intra-plate.
Okay, sir. I see there are a lot of questions. Should I proceed for more?
As you wish, no issue. If I'm not able to answer, then I have a very good expert, Professor K.Gahlaut is here. Then Shantanu also can answer some of them. No issue. Go ahead.
Thank you so much, sir. Do you suggest Indian plate is still subducting beneath Indo-Burmese region?
Oh, very intelligent questions. I'm really amazed. Yes. So this was the story almost like 7 or 8 years back when we said that look, there is hardly any subduction, is hardly any underthrusting of Indian plate below the wedge because the motion on Sagaing fault or the motion on CMF, Chorzan fault, is purely dextral type. So there is no scope of under thrusting. But then when more data came from Bangladesh, and of course then we refined it, then we found that yes, there is some motion, some reverse motion which can be which probably is accommodated through subduction, at least in this part. So yes, this oblique, I mean, these oblique motions are very notorious in that sense that it becomes very difficult to partition them until unless you have huge amount of data, huge coverage. For example, look at Nepal. I mean, Nepal is such a simple case. So you have head-on collision. There's the motion between southern Tibet in Nepal and India is absolutely arc normal. So there's absolutely no arc parallel motion there. So there's no partitioning of motion. So it's very simple, straightforward case. But when the motion becomes oblique to the arc, then we have problem how to partition it and where to partition it. So that requires a huge network. That requires a very good network. And as of now, the other limitation is unfortunately the Bangladesh part is that it's all sediment filled region. So there's you need to really guarantee, you need to really ensure the stability of all the benchmarks. It's not absolute hard rock. There could be, and by the way, this is a region which is where you have lots of influence of delta as well. So there's a delta, there's a tectonic motion, there's delta motion, there's a lot of sediments which are brought by Brahmaputra and Ganga. So there are several processes which are working in that region, and it becomes very difficult to identify the contribution of each and every process. So that's something which we have to live with it. I mean, that's probably with more data we'll be able to confirm, to quantify as to where. And I mean, this is something which we have to live with it. That of course earthquakes kill people, earthquakes cause damage, but it is these earthquakes which give us data, which tells us about the region. So probably in next 10 years, 20 years, if there are more earthquakes in this region, and I only pray that they will not cause any damage, then but then they will give us valuable information about the tectonics. So that's something which we learn with time. So we learn through data, we learn through earthquakes. So with probably in few years time, we should be able to quantify more robustly as to how much motion is accommodated, how much subduction is actually taking place in the sea. Oh, I can't hear you.
Unmute. Ashish, please unmute.
Yes, sir. Yes, sir. These are the questions from the participants, and thank you so much for solving our queries, sir. The remaining questions will be mailed to you, sir.
Thank you.
And now, can we have final comments from Dr. Saurabh Barua? Over Dr. Saurabh Barua.
Yes, Shantanu. Thank you. I congratulate Dr. K.Gahlaut for such a commendable, such a wonderful lecture, I'll say. We are enlightened. And I really take the opportunity to thank on behalf of CSIR Northeast Institute of Science and Technology to Professor K.Gahlaut, the convener of, I mean not convener, but the chairperson of this seminar, Professor Ramesh Singh, and of course Shantanu Barua for this delivering this wonderful platform. And once again, thank you so much, Dr. Pini. That's all I want.
Thank you.
Thank you, sir. Over to Mr. Sustov for vote of thanks. Sustov.
Yes. Thank you, Santanuda. As today's event has come to an end, it is my pleasure to deliver the vote of thanks to one and all. At the very outset, I, on behalf of CSIR-NGRI and the organizing committee of IVWGST, would like to thank Dr. K.Gahlaut sir of CSIR-NGRI India for readily accepting our invitation and deliver today's talk on tectonics of Indo-Burmese arc. Sir, thank you for showering your vast experience and tremendous knowledge upon us and enlightening us in understanding the diverse earthquake characteristics and tectonic features of Indo-Burmese region and northeastern region of India. Thank you, sir. I also would like to extend my heartfelt thanks to the chief guest of today's event, Professor Ramesh Singh of Chapman University, USA, for sparing his valuable time and being present in today's event, despite of his very busy schedule. I further would like to have the opportunity to thank our Honorable Director, Sir, Dr. G. Narahari Sastry of CSIR-NGRI for kind permission and necessary suggestions to successfully organize the workshop. Sir, we are very much thankful to you. I also would like to thank the chairperson of today's event, Professor J.R. Kayal, sir, former DG, GSI, Gulf of India, and co-chairperson, Dr. Saurabh Barua, sir, Chief Scientist, CSIR-NGRI, Jorhat, for their continuous support and guidance throughout the workshop to make it a grand success. I would like to grab the opportunity to thank Dr. Shantanu Barua, convener of this workshop, who took the pain in arranging this workshop and provide us the opportunity to interact with such eminent personalities in the field of seismology worldwide. Not the least, I would like to thank all the participants for their active participation in today's event, without which this event would not be a success. Thank you all. With this, I conclude and wish you all a very good day ahead. Thank you.
Thank you.
Thank you. Thank you, Benny.